So we gonna talk about how you can finish assignment 4 here. Okay, so first we need to understand some basic, right? So we talk about priority queues, heaps and grabs, right? So a priority queue is a data structure that you let the one that has highest priority go first, right? For example, if I go to visit a doctor, I'm on the line, but maybe another patient has more emergency, then he can go first. Now the question is, same thing with the data that we store here. Some data has higher priority, and how we gonna handle that? So there are many ways to implement a priority queue, right? We said an unsorted list. When you dequeue, you would require to search through the entire list, right, for the priority, right? We can use an array-based sorted list, and we know that array-based when you enqueue is expensive, right? And reference-based sorted list, reference-based means use linked list. Again, when you enqueue, it's going to be ON. How about BST? We know on average our BST is going to be big O log n's, right? For both NQ and DQ. But that's on average. It's not always guaranteed it's going to be log n. Because BST has to be balanced, right? In order to be log n, right? Has to be balanced tree. So we gonna look at a heap. How about heap? Heap actually guarantees always log n steps, even the worst case. So let's look at what's heap. Heap pretty much is an implementation of a priority queue based on a complete BST or binary tree. So, and it has to be complete. So that means either almost like a triangle, right? Or yeah, triangle shapes, right? Like if you look at this is a complete, right? We cannot have like leaning toward one directions, right? Now, also we said BST, we said left is less than the root and right is greater than the root, right? Left is less than equals to root. But for heap, value that is greater than or equals to the value of each of its children. So that means the top is higher than the bottom instead, right? So different rules. So in order to have the heap for the priority queue BT here, we need to keep two properties. Shape has to be complete, and order, right? The node, parent node is greater than the children nodes, right? So there are two properties for the heap. So let's look at an example. So this is a heap because the shape is complete, and this is the BT, right? And pointer point to the heap, and you see J is greater than H and I. H is greater than D and G. I is greater than F and A, and D is greater than B and C, as well as G is greater than E. So this is a heap. And heap can be another heap here, right? Can be any order of letters here. As long as J is greater than I and G is greater than E and B, and I is greater than H and F, and vice versa. Now let's look at the DQ operations. The DQ, we pretty much Like I said, this is a priority queue. When you dequeue, the one that has the highest priority go out first, which is J. J has the highest values, which is highest priority, right? Then J is going to be removed first. After remove, we break the shape. Then we have to reshape it, right? So we call reheap methods, right? When you dequeue, you have to reheap, right? So reheap, we call reheap down because we have to keep the shape property. In order to keep the shape property, you have to remove E, right? Then we still have complete. And we put E on the top where J is gone, right? Then we're going to worry about the order property by reheap down, moving E to the right location. Move it down to the tree. So for example, after we keep the shape property in B here, we put E there. Now we start to compare H and I. Right, E is lower than H and lower than I, right? So we need to swap, right? So in this case, it happened to swap between E and I, right? So I go up, and then E compared to F, right? Again, why we want to do I? Because I is greater than H. You can't swap E and H. Because if H go up, then it's break the order property. So that's why we have to compare H and I, who is greater. I is greater, that's why I go up. And then it's going to reheap down to right. Now we found that, okay, F is greater than E, so we just reheap down E again. Now we got our heap back, which is complete shape and order is good, right? Parents always greater than children. When you do DQ again, same thing. Remove I, put C there, right? And see if F and H, which one is greater? C, H, and F. Take the greater one to the top. In this case, H is going to go, right? If I remove I again, and C go down here, right? And then compare again D, G, and C. So G is greater, or D, G, then G go up, and C is there. And then we done. And we still have complete, and order is correct. So that's how we DQ for heap. So we are depending on reheap down. How about NQ? When you want to add something into the heap. So, for example, we're going to add K. So K is adding to the heap. So when we add, we're just going to have a placeholder, right, a blank, because K is not going to be there. The one that's going to be there is the one that's smallest. K is higher than G. So we have to reheap up, right? Move this placeholder up, and G move down, right? So placeholder right here now. And look at K and H. K is still greater than H. So move H down, right? And reheap up. So placeholder go to H. K and M. Now K less than M, then that's the place for K. And we have the order property and shape property, we still have heap back. So that's how we NQ.